This is our conceptual HVAC design for Lagos, Nigeria. I'm Katherine Howell and working with Parker Zwerenz and Donovan Smith. For our table of contents, we're going to start out with climate analysis, go on to electrical considerations, and then potential HVAC systems, our final conceptual design, and last, architectural layout. For our climate analysis, as you can see, Lagos is very hot year-round and also very humid. The average monthly high is between 35 and 27 degrees Celsius, and the low never reaches 20 degrees Celsius. The high rainfall centered around June, along with the coastal location, means that the relative humidity hovers around 80% all year long. Further analysis, there are low wind speeds and heavy cloud cover year-round, and because of the consistent climate, the ground temperature hovers above 25 degrees Celsius, even 4 meters beneath the surface. You can see on our psychrometric chart, 0% of the time is naturally spent in the thermal comfort zone, so we have to dehumidify and mostly cool in order to get any thermal comfort in Lagos. For electrical considerations, the national grid of Nigeria is unfortunately unreliable. Even in urban regions or areas, they only have electricity about half the time or occasionally. And for Lagos specifically, the grid provides only 10% of the state's demand. Lagos itself produces 15,000 megawatts off-grid from generators, and recently they've initiated the Light Up Lagos Community Electrification Program to try and establish an electricity market and encourage the use of renewables. For our own renewable energy, low wind speeds unfortunately mean that wind renewables are not an option, and despite the high cloud cover, there is a lot of national and regional investment in solar panels, so that is what we chose. We can meet about 60% of our energy demand that we estimated for our building with photovoltaics on 75% of the roof. And we want to have a battery storage system in order to make sure that when the grid goes out, our building does not. For potential HVAC systems?
Yeah, so the HVAC systems that we used, we wanted to use an ERV to both cool and humidify the entering air, and without using any electricity, just by using the exchange with the exhaust air. We also wanted to use cooling coils to cool and dehumidify the air, and then also use fan coil units to just provide additional cooling as needed. Something interesting that we wanted to use a heat pump water heater in each of the units, as this is going to both reduce the cooling load in unit and supply the hot water needed for the unit. So sort of a double whammy there as far as reducing the electricity we need. As for systems that we didn't use, we looked into geothermal heat pumps. But we ultimately decided that the climate isn't moderate enough for heat pumps of that scale to be efficient. We also considered an HRV, but chose an ERV over the HRV to reduce that humidity of the entering air. We also looked at desiccant cooling systems, but we opted for both cooling and dehumidification together. And then since we are using solar panels on the roof, we did look at PV heat recovery. But we ultimately decided that since our heating load is negligible and we basically just need hot water for showers and personal use like that, we decided not to go with that system. So for our final design, here we have a path of the airflow as it goes through the building. So entering air starts by entering through the ERV, exchanges with that exiting air and dehumidifies. It then mixes with the return air. We didn't want to use a dedicated outdoor air system just because we wanted to utilize the air that had already been cooled and dehumidified. We then go to the cooling coil, which removes that humidity and cools it even further, and it's applied to the zone. We do have additional cooling within the zone. We have the air source hot water heaters that should take about 1 kilowatt of heating out of that cooling demand. And then we also have in-unit fan coil units as needed. So while we didn't necessarily do any hard calculations as far as the changing loads throughout the year, all of that, we did want to sort of go into ease and graph whether or not this was feasible. So if you look along the purple lines, we have the exchange between the entering outdoor air and the exiting exhaust air. And then that air goes down, mixes with our return air along the orange lines, cools along the cooling coil, and then that green line is the air mixing inside the zone. And that gets us towards the yellow star at the middle, which is within that comfort zone.
And then here are a few of the appliances we talked about previously. On the left, you'll notice that ERV. In the center, there's a Daikin fan coil unit within each apartment unit. And then on the right is the heat pump hot water heater that we thought would be wonderful. It's 50 gallons. Here, you'll see our architectural layout for each unit. The way that this works is we sandwich our energy pod in between both the living room with the kitchen and the bedroom with its bathroom. This allows for short piping to reduce the losses through that network, as well as its location of the corridor, allowing for maintenance to access this energy pod without entering the unit itself. And within this energy pod, you'll see our HVAC equipment, our battery storage system, and then that heat pump hot water heater. Below, you'll see a floor plan by floor. It's essentially that same unit, just repeated over and over again. We have a total of 40 units in this building. On the roof, you'll see that most of the roof is covered with PV panels. As Katherine mentioned previously, approximately 75%. You'll see RTU units with that ERV as well as the condenser. And then you'll see a low slope roof. This allows for a lot of our roof to be covered with PV. And then within each unit, we did want to consider solar heat gain, as well as the occupant's ability to allow for passive cooling. So there's some narrow operable glazing. We wanted to thank you for taking the time to hear our HVAC solution for Lagos, Nigeria.